CanESM6 Just prior to kicking this off, even though we're on a remote platform, I do also want to take a moment to acknowledge the Indigenous people of all the lands that we are on today, from coast to coast. We acknowledge the ancestral and unceded territory. Oh boy, sorry. I just started to be able to hear myself. I'm gonna mute. Great. Okay, sorry. Yeah, from coast to coast, we acknowledge the ancestral and unceded territory of all the Inuit, Métis, and First Nation people that call this land home. And with that said, we can kick off. So I just want to give a note to all the instructors. For the first presentation, we will be doing 30 minutes, Dr. Ivy Tan. And then after that, we will adjust the schedule that I've shown on screen to adjust back by 15 minutes. And for the 30-minute talk, Ivy, I'll be giving you a warning at 20 minutes, and then everyone else will give you a warning at 10. And then so we can still have some time for some questions. With that, I will kick it over to you, Ivy, and I will stop sharing my screen if you want to load yours up.
Okay. Can everyone see my screen?
Yeah.
Okay, great. So I'm gonna okay, so I just wanted to make sure. Can you see the slide by slide?
Yes, we can see it in like scrolling mode right now.
Okay. Okay. Is it okay though? Is this view?
I think that works okay if you can't put it into presentation mode.
Okay, I'll just get started in this mode then. Okay. All right. So good afternoon, everyone. It's great to speak here today in this session on collaborative Earth system modeling in Canada. And I'd like to thank the session organizers for the invitation. So my research group uses Earth system models as a key tool to understand and diagnose the role of climate feedbacks, especially clouds in climate change. And in considering the topic for my talk today, I decided to present work that's of broad interest to everyone. And that is the climate sensitivity of the Earth based on what Earth system models project. So before I start, I'd like to thank my co-authors here for their contributions. Okay, so I'd like to open with the fact that Earth system models unanimously agree that Earth's global mean surface air temperature rises in response to a doubling of atmospheric CO2 concentration. So there's no doubt about that. However, what Earth system models do not agree on is the extent of global warming in response to that doubling of atmospheric CO2. And this ultimate warming in response to CO2 doubling is a metric known as the equilibrium climate sensitivity, or the ECS for short. And according to the IPCC's sixth assessment report, the best estimate of the ECS is currently 3 degrees Celsius, and that's based on multiple lines of evidence, including Earth system models, but also the historical climate record and the paleoclimate record as well. Now, interestingly, the CMIP6 models, which are the newest generation of Earth system models participating in this international intermodal comparison project. So these went into the best estimate in the IPCC report, and they exhibit both a higher mean and a larger spread in these ECS values compared to the previous generation of climate models that participated in CMIP5. So this obviously begs the question of what causes that larger mean and spread in the ECS values in CMIP6. And it turns out that clouds are responsible for the warmer ECS values in CMIP6 Earth system models compared to CMIP5. And in particular, a study showed that clouds exacerbate global warming because they reflect less sunlight back out to space. But what might cause clouds to reflect less sunlight back out to space? Well, a decrease in the opacity of clouds, which I'll denote by the Greek letter tau for the rest of this talk, is a key reason for why clouds might reflect less sunlight back out to space in response to global warming. And this makes sense because optically thick clouds tend to act like a reflective blanket that deflects any sunlight that reaches it right back out to space. And this change in cloud optical thickness in response to global warming is what's known as a cloud optical depth feedback, which I'll denote by lambda sub tau for the rest of this talk. So to illustrate this lambda sub tau feedback, let's consider two different clouds reacting to a global warming scenario here. So the cloud on the left-hand side is optically thicker in response to global warming. So it reflects sunlight out to space more effectively, and it shields the surface from absorbing it. This is a cooling effect that acts as a strong negative feedback that counteracts global warming. On the other hand, so we have this cloud on the right-hand side, which is also optically thicker in response to global warming. However, it's just not as optically thick compared to the cloud on the left-hand side. So all else being equal in this situation, the cloud optical depth feedback, lambda sub tau, is still negative, but it's just less negative than what it is on the left-hand side. Okay, but now what makes a cloud optically thick? So multiple factors are involved, including the water content of the clouds, the size of the particles that make up the cloud, and also the vertical thickness or extent of the cloud itself. But of these factors, for mixed phase clouds at least, that contain both supercooled liquid droplets and ice crystals in them, probably the most important large-scale control over the opacity of these clouds is the percentage of them that's comprised of liquid. So in other words, the supercooled liquid fraction, or the SLF, of the clouds exerts a strong important control over the opacity of mixed phase clouds. So to summarize this, a cloud with a higher proportion of liquid in them, so they have a higher SLF, they're also optically thicker, and conversely, a cloud with a lower SLF is optically thinner. So it turns out that most of the Earth system models participating in both CMIP5 and CMIP6 show an increase in the opacity of extratropical clouds in response to global warming. And this shows up as a negative ensemble cloud optical depth feedback parameter, lambda sub tau here, which is actually more negative for the CMIP5 models overall, especially in the extratropics as shown on the left, compared to the CMIP6 models here on the right. We previously showed that the cloud optical depth feedback was linked to the SLF of mixed phase clouds in the pre-warmed climate state, and we demonstrated this using the American CESM model. So what we did was we ran a set of 5 experiments with a wide range of SLF in the mean state, holding the atmospheric CO2 concentrations fixed to present day levels. And then what we did was a global warming experiment where we doubled the atmospheric CO2 concentrations instantaneously. And what we found was that the cloud optical depth feedback in response to global warming became increasingly less negative, or equivalently, I can say that it became more positive as the SLF of the pre-warmed climate state increased. So this is illustrated here. When mixed phase clouds in the pre-warmed state are optically thinner, so in other words, they have low SLFs, which is shown by the fact that the clouds are whiter here going towards the left in the top row. The cloud optical depth feedback parameter, lambda sub tau, in response to global warming, which is shown here in the bottom row, it becomes increasingly more negative, shown by these darker blue colors. And so as the clouds get optically thicker in the pre-warmed climate state, so now we're going from left to right here, lambda sub tau also becomes less negative especially in the extratropical regions here, including the Southern Ocean, where mixed phase clouds are ubiquitous. So the mechanism explaining this phenomenon is known as the cloud phase feedback. And in this feedback, an initial CO2 doubling causes the atmosphere to warm and the troposphere to deepen. So this in turn implies that isotherms are shifted upward in altitude, which leaves behind a layer of liquid where there was previously cloud ice at a given altitude. And this replacement of ice with liquid as we discussed, increases the optical thickness of the clouds, making the clouds more reflective to sunlight, cooling the Earth, and therefore counteracting that's initial global warming perturbation, making the feedback negative. So tying this back in with the previous slide here, recall that starting off with higher SLFs in the pre-global warming state will always result in a weaker or less negative, sometimes even positive cloud optical depth feedback in response to global warming. So you can basically think of these clouds here with the higher SLFs as having a cloud phase feedback that's already saturated. And so there's less potential for liquid to replace ice in the cloud phase feedback. Okay, so the main punchline here is that this SLF lambda sub tau relationship that we just saw via the cloud phase feedback is so large that it can strongly influence the ECS. And so you can see this here. There's a strong correlation between higher SLF states in the pre-warm climate and higher ECS values post-global warming. And this plot here summarizes that SLF lambda sub tau relationship in CMOS that can be explained by the cloud phase feedback. And I note here that the R squared value for this linear relationship is very high. In addition to the CESM model, we also found the same relationship holds in the GEOS5 model, although I do note that GEOS5 is technically not a CMIP or system model. This plot here shows going from right to left now that lambda sub tau becomes less negative as the SLF of the pre-warmed climate state increases. And here the SLFs are color-coded so that the cooler colors, green and blue, represent the lower SLF states, and the warmer colors here, yellow and red, they're color-coded to mean higher SLF states. So this plot here also shows, in addition to this, the change in cloud liquid water path in response to global warming on the x-axis. So the fact that larger cloud water increases are associated with lower SLF states and also more negative cloud optical depth feedbacks, lambda sub tau, is also consistent with the cloud phase feedback. And I also note here that the R squared value for this linear relationship between lambda sub tau and the change in cloud liquid water path is very high in this model. So given the strong correlation between SLF and lambda sub tau here in these two Earth system models, a natural next question to ask is, does this relationship hold across all CMIP5 and CMIP6 Earth system models? So for CMIP5, we found this not so much to be the case. There is a rather weak correlation between lambda sub tau and SLF, although I note that this is still work in progress, so we're getting more models in this analysis, but also that there are a couple of models here that really throw off that correlation that would otherwise be much stronger. For CMIP6, we're finding that the correlation is much stronger, and it's also consistent with what we'd expect from the cloud phase feedback, again, except for these outliers here that would otherwise make the correlation much stronger. And I note here, maybe I should point out the CanESM model here. So CanESM is here for CMIP6, and for CMIP5, it's also somewhere in the mid-range value over here. Okay, so why are we concerned with these linear correlations? Well, these correlations are more useful than just supporting the importance of the cloud phase feedback and climate change. We can also use these correlations to constrain future climate change. This is what's done with the emergent constraint method, which has been used quite extensively to constrain uncertainty in the CMIP5 and CMIP6 Earth system models. So here's how that framework works. If one of the variables is well observed and therefore easily constrained, so let's suppose that that variable here is on the x-axis, and let's say the other variable that's well correlated with it on the y-axis here is a variable that's associated with future climate change that's highly uncertain. So it exhibits some prior intermodal uncertainty here. Well, what we can do then is use the observed variable to constrain the future climate change variable. So in this diagram, let's suppose that the observed range in the x-axis variable is this blue shading here, and that each red dot represents an individual Earth system model that's part of CMIP 5 or CMIP 6. So the emergent constraint method says that all of the Earth system models here outside of this blue shaded region can be ruled out as being unrealistic. So they're not realistic. So that's how the emergent constraint framework works, but there's a caveat to it, and that is that these relationships have to have some sort of underlying physical mechanism behind them. And the reason for that is because correlation naturally doesn't imply causation. And so any relationship between the two variables could technically be fortuitous. So just to illustrate that emergent constraint method here with a concrete example, consider this tight correlation here between the seasonal cycle and surface albedo. So that's on the x-axis, and the long-term surface albedo feedback, which is on the y-axis. And this is shown for the CMIP 3 and CMIP 5 models. Because the seasonal cycle in the surface albedo change is observable, so we can get those, for example, from present-day satellite observations. So let's say that the observed value is this vertical black line here, and its associated uncertainty is this gray shaded region. Then the emergent constraint method basically would rule out all of the Earth system models outside of this gray shaded region and says that their values here in the albedo feedback are unrealistic. So what we did was we modified the emergent constraint method to yield a more quantitative constraint on the ECS, even if neither of the variables that we're correlating is the ECS metric itself. So our method here is based on the traditional so-called forcing feedback framework, where we have N here. This is a net radial flux imbalance at the top of the atmosphere, and it's equal to F, the radial forcing, plus the product of lambda, which is the climate feedback parameter, and delta T sub S, which is the change in global mean surface air temperature. So since this is a linear equation, we can plot N here, average for each year globally as a single data point. We can plot it here as a function of delta T sub S. And I'm using an individual Earth system model here, CanESM5 as an example. And so we can see that from this plot here, the y-intercept of the plot represents the rate of forcing. The slope here is the climate feedback parameter lambda, and then the x-intercept is the ECS. And so for the CanESM P1 model that participated in CMIP 6, the forcing feedback framework gave us an ECS of about 5.6 degrees Celsius. So let's focus now on this lambda net climate feedback parameter here. So lambda is actually the sum of all feedbacks acting within the climate system. So this includes the Planck feedback, the lapse rate feedback, the surface albedo feedback, and the cloud feedback as well. But the cloud feedback is actually decomposable into further components. So we have our good old lambda sub tau variable here that we know is biased because of its large spread, as we saw earlier. But there are also other cloud feedbacks as well due to changes in the horizontal extent of the clouds and also the height of the clouds. So just as a side note here, typically we use what's known as the radiative kernel method to calculate these feedbacks. And this assumes a first order Taylor series expansion. But we know in reality that feedbacks, especially under large climate perturbations, are rarely linear. So the error associated with that assumption in the linearity of the feedbacks is captured by the residual terms here in equations 3 and 4. So now given that SLF lambda sub tau relationship we saw earlier, if that relationship holds across all CMIP models, then we can use modern satellite observations to quantify the bias in SLF. So let's call that delta SLF. And we can calculate the bias for each individual model, which is denoted by the subscript I here. And so if we differentiate equation 6 here, then we can get the bias-corrected lambda sub tau here in equation 8. So what we can do with that is feed that back into the equation for ECS using that forcing feedback framework and calculate now the adjusted ECS for each individual Earth system model. So this final equation here is our new method for adjusting the ECS for each Earth system model to account for biases in the cloud optical depth feedback via its relationship with SLF. So to summarize our method in this diagram here, so we start off with our emergent constraint-like diagram where we have lambda sub tau as our future climate change variable on the y-axis, and we have as our observable present-day variable SLF on the x-axis. So the observational range in SLF is shown by this green shaded region here. And this means that all of the Earth system models to the left of it in the blue shaded region contain too much ice in their mixed phase clouds. And all of the Earth system models to the right of the green shaded region in the orange shading here, they represent Earth system models that have too much liquid in their mixed phase clouds. And so the emergent constraint method would rule out all of the Earth system models outside of this green shaded region. So it would only keep 2 of these models here, whereas our method, on the other hand, takes each individual Earth system model and it adjusts the ECS value for that model to a new value that accounts for corrections to biases in lambda sub tau. Okay, so before
applying,
sorry?
20-minute warning.
Okay, thanks. Okay, so before we apply that method, we will first look here at the SLF for the actual observations. So for this, we use a product that's derived from global satellite observations called GoCCP. And this GoCCP observational product was actually designed to be compatible with Earth system model analysis. So we defined a metric T50 in place of SLF to represent the global SLFs. And this T50 is basically the temperature at which half of the clouds are glaciated globally. So warmer T50 values means that there are actually lower SLFs, and then colder T50 values means that there are higher SLFs. So for the GoCCP observations, T50 is about minus 14 degrees Celsius. And actually, sorry, I just realized that I had CanESM2 here. That's not showing up on this slide, but for the 2 versions of CanESM, so you'll have to trust me for CanESM2 here. So these 2 models, I'm pleased to announce, actually produce T50 values that are in close agreement with the GoCCP observation. So they're around minus 14 and minus 15 degrees Celsius. And CanESM5, which participate in CMIP6, actually produces just slightly more liquid overall compared to CanESM2, which is not showing up, but which participated in CMIP5. Okay, so for the rest of the CMIP Earth system models, and I note that this is still work in progress, we're finding that overall, for the CMIP6 Earth system models, they tend to simulate higher SLFs compared to the CMIP5 Earth system models, and this also includes CanESM to a small degree as well, as we showed in the previous slide. And the SLFs, the higher SLFs in CMIP6 are actually reflected by the fact that the mean T50 is lower compared to the mean T50 value for CMIP5. And we can also see that the mean T50 values for the CMIP Earth system models is also lower compared to the GoCCP observations. So this means that the CMIP6 Earth system models tend to produce too much liquid relative to ice, even in comparison with the observations themselves. Okay, so just as an aside here, that's relative to collaborative Earth system modeling in Canada. It's interesting to note that CanESM, despite having relatively simplified representations of cloud microphysics, actually represents the global T50 values quite realistically. Currently, the simplified microphysics in CanESM are in the process of being revamped to more sophisticated cloud microphysics. And in future work, we plan to collaborate with ECCC folks to improve some of those parameterizations in cloud microphysical processes. And we plan to use some of these empirical observations that my former postdoc, Quentin Koopman, had analyzed based on spaceborne LiDAR and radar observations. So he quantified the variability in cloud liquid and cloud ice pixels within a model grid cell to basically guide the improvement of cloud microphysical parameterizations in models. And we're currently testing the parameterizations out in the American CESM model and hope to do so as well in the collaborative version of CanESM in the future once the cloud microphysics schemes have been implemented. And I just saw Jason Cole earlier today, and he told me that the work on improving the cloud microphysics is starting today, actually. So the postdoc working on it is starting full time on it today. So now getting back to our key results here of our project. So after applying our method to adjust for the ECS values of individual Earth system models to take into account those biases in lambda sub tau, for CMIP5 on the left-hand side, we're seeing that adjusting for biases and underestimating the SLF and mixed phase clouds, it slightly adjusts the ECS of the models upward to 3.4 degrees Celsius. For CMIP6, on the other hand, on the right-hand side, we see that adjusting for biases and overestimating the SLF in mixed phase clouds, they slightly decrease the ECS downwards using our new method. So the new adjusted mean for CMIP6 is 3.7 degrees Celsius. It's also interesting to note that the adjustment to the ECS values that we did using our new model decreases the number of CMIP6 Earth system models with high ECS values that are over 4.5 degrees Celsius, down from 8 to 5. And so the net result is this upper range moderate ECS value. So to conclude, I have 3 take-home messages from my talk today. The first is that the CMIP6 Earth system models produce a greater fraction of supercooled liquid in their mixed phase clouds relative to CMIP5 Earth system models. And also the CMIP6 models, however, are unfortunately unrealistically high. They produce too much liquid in their mixed phase clouds compared to the actual observations by satellite instruments. Second, we developed a new method to constrain the climate sensitivity of Earth system models by correcting for biases in the cloud optical depth feedback parameter. And application of our new method suggests an upper range moderate climate sensitivity of 3.4 degrees Celsius for CMIP5 and 3.7 degrees Celsius for CMIP6. So with that, I'd like to thank you for your attention, and I'd be happy to take any questions.
Thank you, Ivy. Yep, anyone, if you have any questions, feel free to post them in the chat during the Q&A on the EventMobi site, and I will happily read them aloud.
I don't know. This is Paul Kushner here. I don't know if I can ask a question just directly, or I don't see any questions coming up in the chat or the EventMobi or the Q&A. So
no, I don't see any. Go for it, Paul. Go for it.
Okay, I'll go for it. First of all, thanks a lot, Ivy, for a really nice talk. Lots of interesting results there. I was going to just start with the last one because you made this interesting point about CanESM having this realistic shortwave cloud optical depth feedback, if I understood correctly, or its constraints were sort of matching observations. But it is one of the higher climate sensitivity models. So just to kind of come back to CanESM a little bit, when you did those corrections, did it actually when you applied the emergent constraint, did it actually how did that affect the estimated sensitivity for CanESM itself? Do you know?
Right. So for CanESM, so that's a great question, Paul. With the supercooled liquid fraction that was constrained by the observations say that CanESM has a pretty good estimate overall. However, its climate sensitivity was rather high. So if we were adjusting for mixed phase processes alone and adjusting for the climate sensitivity based on that alone, CanESM5 actually didn't change much in terms of that,
Right.
because it was assumed to be quite realistic. So it didn't change much. Maybe I should have highlighted CanESM as well in that distribution, but the high ECS values were basically attributed to other processes rather than the cloud phase itself. So if we're accounting for just mixed phase processes, CanESM was actually not doing too poorly, actually was in quite good agreement with that. But I do expect that to change, at least going forward now with the new microphysics scheme in the models, implementing 2-moment microphysics and P3 microphysics as well. I do expect that to change. So it'd be interesting to see what happens with the model afterwards.
Thanks.
Thanks, Ivy. In consideration of time, we will be passing over to Carsten Abraham now to present on the Canadian atmospheric model version 5.2. Ivy, I will note that there is also another question in the Q&A if you want to just take a look at that and respond in text. Carsten, if you can share your screen and we can get going here whenever you're ready.
All right, can you hear me?
Yeah, we can hear you. Yeah, if you want to move over to presentation mode and then we can get started. Thanks, Carsten.
All right, thank you for letting me speak here. I'm going to present work on the Canadian atmospheric model, version 5.2 now, which is our latest physics update to the Canadian atmospheric model. And just to warn you directly from the start, it's a version that we have frozen early May of this year, so it's really our bleeding edge of development. And we haven't tuned it up yet, so it's not ready for scientific use and it's not ready for operational use. But we still wanted to present you the updates on the physics side that we've been doing over the last couple of years. I also want to acknowledge that this is work from the whole Canadian Centre for Climate Modeling Analysis Atmospheric Physics Working Group. So it's a number of people, and everybody, including the technical staff, have been tremendous work on this. So just to give you a quick overview, the Canadian atmospheric model is a core component of the Canadian Earth System model, and it basically models and simulates all atmospheric processes. Currently, we have representations in that model for gravity waves, the general dynamics, convection, aerosol, chemistry, clouds, radiation, and atmospheric boundary layer physics. And all of those parameterizations, or the model itself, has been always developed in-house within the CCCMA, or in close collaboration with CCCMA staff, which until today makes us quite a unique model amongst the Earth system model that contribute to CMIP. So if we're looking at the family tree of all the CMIP models, there's CanESM and with its atmospheric component CanAM, and you can see that we are kind of a unique model out there. Yeah. If we go a little bit through the history of the Canadian atmospheric models, so our last major physics update happened in 2011 or 12, I believe, and was published by Clint in 2013, and it was part of the CMIP 5 contribution with CanAM 4 at that point, here on the top left-hand side. As we moved to CMIP 6, we had some minor updates, I would say, to the atmospheric model, and particularly we had updates to the land-surface atmosphere interaction, which I'm going to in detail in a couple of minutes. But now we went towards CanESM 5.2, which has a real update to some major physics parameterizations within the atmospheric model. And it will be basically the basis of CanESM 5.2 will be used for CanESM6, which will be our CMIP7 model, hopefully. And Neil was going to talk about this later in the session, and I encourage you to stay around for that. So if we're looking at CanESM 4, as I said, it was the last major physics update. We changed particularly the resolution and the vertical resolution. So we changed at that time from 35 to 49 levels. We did some major updates to the radiation code at that time. And we had new aerosol updates with it, with better microphysics and interaction of bulk aerosol dynamics with radiative transfer, for example. As we went towards CanESM 5, so our CMIP6 contribution to the physics itself, we had minor updates. So we did some tweaks to the radiation or the hydrology, but particularly we went towards having tiles on the land surface side, so we got a better representation of the subgrid scale interaction between surface and the atmosphere, for example. And we also included a new hybrid tracer tuning, which helped a little bit with some of the traces. But as we're going now towards CanESM 5.2, we get an update of some of the major physical parameterizations. So we get a new radiation code with a new correlated K distribution. We have a 4-stream radiative transfer approach now. We rewrote basically the whole atmospheric boundary layer scheme, and it's based now on the turbulent kinetic energy budget, or it's the turbulent kinetic energy budget equilibrium. We are going to include, or we have included, a new land surface model, Classic, which is based on the old one, and Vivek is going to talk about this directly after this talk, so I'm also encouraging you to stay around for that. And I'm not going into any details from that, as Vivek can explain that much better than I. We updated our deep convection code, which has now a better interaction, first of all, with the environment. So we introduced adaptive entrainment and detrainment rates, and we have also a new prognostic closure scheme for the deep convection. Also, optionally, we have now the piecewise logarithmic approximation aerosol model, so PAM, in the model, which can be used for scientific use. Basically, we are not sure whether we can turn it on operationally, but it is definitely an option that can be used in future for scientific research within the CanESM 5.2 physics. So let's go a little bit into detail on all of those 4 parameterizations or 4 updates that I've talked to you, so that you can see how our model reacts to it. And again, it hasn't been tuned yet, so there's not a real bias, or we haven't reduced really the biases completely, and it's really just an overview. So we introduced the updated correlated K, or we updated the correlated K distribution. We have the 4-stream radiative transfer implemented, and in radiative transfer codes, you can compare basically your new schemes with line-by-line calculations on 100 profiles, which are shown here on the right-hand side from the RF MIP. And if we're looking at how the radiation code is working in comparison to those line-by-line calculations. So here we're looking on the left-hand side, or the left column, at the solar absorption within the atmosphere, and on the right-hand side on the thermal absorption of the atmosphere. On the y-axis, we always look at the bias towards those benchmark profiles from line-by-line calculations, and on the bottom you can see some reference fluxes depending on those sites. And I would like to draw your attention to the blue dots and the red dots. So blue is CanESM 5.1, which is our previous version, and 5.2 is now the updated version with the updated radiation code. And you can see that particularly in the solar absorption within the atmosphere, so that's the top left-hand panel, we can reduce those biases, particularly for large radiative fluxes. And particularly also in the stratosphere, so this is the bottom left panel, we're looking here at the solar absorption of the atmosphere above 50 hectopascals. And you can see that for larger fluxes with the new radiation code, we get much, much closer to the line-by-line, or we are pretty good in comparison to the line-by-line calculations, whereas before we had huge biases So plugging those into our current version of CanEM, so CanEM 5.1 is on the left-hand side. That's our current operational model. You can see that we have those, we're looking at the cross-section of the atmosphere, and you can see those warm biases, particularly in the stratosphere, which come from the absorption biases in the solar radiation, as we have seen. So just using the same model with the new radiation code on the right-hand side, you can see that basically we are cooling now the stratosphere. Again, it's not been tuned, but you can see already that the direction of the sign is in the right, or that we correct into the right direction with this new code. As I said, we updated the atmospheric boundary layer physics. So for decades, we had a first-order closure scheme in our model, which means that the diffusivities were derived from heuristic length scales. So this is basically still based on a Boosting and Dyer parameterization, and we had relatively old stability functions based on the gradient-Richardson number. And we introduced now a completely new vertical turbulent transport model, which is based on the turbulent kinetic energy budget, which means that we find, or that we model an equilibrium between the shear production of turbulence and the buoyancy destruction of turbulence. And we also introduced some extra entrainment at the entrainment diffusivities at the top of the boundary layer, as our model was usually not sufficiently diffusive in the vertical. And we also included new stability functions for the stable branch of the relationships. And here, looking again at the comparison between CanEM 5.1, so the previous version, and just plugging in now the new turbulence transport scheme, you can see that here in the cross-section of specific humidity, particularly in the tropics on the left-hand side, you see that we always had this huge positive bias in the tropics, as we didn't have enough vertical turbulent transports and we couldn't move tracers, for example, out of the atmospheric boundary layer. And just plugging in now this new scheme, you can see that we can reduce this bias substantially. Going towards the new deep convection code or deep convection update, we introduced a new closure scheme in which we relate better the kinetic energy that is associated with an instability and the mass flux through the deep convective cells. The work is now more related to LES simulations and it's much closer to what we believe reality. And we introduced a different scheme for the exchange with the environment and some extra microphysics. So we have now an adaptive entrainment and detrainment rates, which depend actually on the vertical velocities and the vertical change of mass flux within a deep convective cell.
Just a 2-minute warning, Carsten.
Thanks. So that means that we get a better interaction with this environment. We included also ice phases within deep convective cells, which means we introduce an extra latent heat release, and our deep convective cells are able to rise higher and also interact with the tropopause and sometimes overshoot in the stratosphere. And we assume that the downdrafts do not need to be saturated anymore, which was an assumption that we used before, and from which we also diffuse more moisture into the troposphere, and we include a very simplified Berger and Findeisen process, which helps us with the microphysics and the precipitation coming out of deep convection. So if we're looking again at the cross-section here of temperature, and now I would like to draw your attention to the warm bias that we usually had near the tropopause, around 100 hectopascals. Just putting in now the new deep convection code, you can see that we can reduce this bias substantially, and also the new deep convective code in its current version is able to export more moisture into the troposphere and then also diffuse it more within the troposphere. In terms of the precipitation, here on the bottom left-hand side, I'm showing you the frequency of precipitation events in the tropics. In black is the model. In blue and red, you can see GPCP and ERA5 respectively, and you can see that we always had an overestimation of large precipitation events. And with the new microphysics, we fixed that a little bit. We're not there where we wanted to, but we're getting closer. So in the interest of time, I'm just skipping very fast through the option of turning on PEM, so the piecewise logarithmic approximation, which means that we are now able to mix independently black carbon and organic carbon, and black carbon, organic carbon, dust and sea salt can actually interact with clouds. So there's a real aerosol cloud interaction, which also affects cloud droplet number distributions, and we can simulate auto-conversion rates. And as you can see here, so on the top bulk, that's our old approach, whereas PEM is the piecewise logarithmic approximation aerosol model. You can see that we can reduce biases in the absorption optical thickness. Or if we look at the cloud droplet number distributions, we had always large negative biases over the continents, and they are now tremendously reduced by turning on this new submodel. So in summary, CanEM 5.2 is a major physics update that we developed over the last couple of years, and it will be the basis for our CanESM6 contribution. And we hope to release it tuned late summer or early fall this year. And just to remind you, we updated the radiation code, the boundary layer physics, the convective code, and we implemented PEM. So thank you very much. And here are some references if you are interested in reading more about it.
Thank you, Carsten. So we have about a minute or so. If people want to ask some questions, we'll give it a moment. Please fill out in the Q&A chat, and I'll read them off here.
Sorry to be a pain here. I'd quickly rattle out a question. Thanks, Carsten. A lot going on and really exciting stuff. I just wanted to check that it looks like the stratosphere, but like overall the stratosphere improved, but it went kind of on the cold side. And do you have a sense of where that is? I don't know if that's correct, but that seemed to be in that figure you showed. Is there a sense of like why that sort of systematic change happened because of the associated with the new radiative transfer? And I could be wrong, but it looks like there's a lot more blue. So
exactly, yes. So as I try to explain relatively fast, here on the bottom left-hand side, you can see the solar absorption above 50 hectopascals. And before we had way too much absorption, so before we had the blue line. And so we brought it now down to more realistic, or we brought it in harmony with the line-by-line calculations.
Wow.
And as
that's really that's a large. I didn't. I was looking at all the details, so that's really good. Okay, really interesting. It's quite a good attribution then.
Yeah, and so as I said, the model is not tuned yet. I'm just showing you these plots to show you that we are moving in the right sign direction with most of the things.
Right.
But we are currently in the process of just tuning up the model, and hopefully then we can release a model version where there's a much smaller bias in general in the stratosphere.
Yeah. This is a bias relative to something?
This is a bias relative to ERA 5.
Okay, and the CO2 concentrations you're using are?
And this is in development run from 2003 to 2008.
Okay, thank you.
Yeah. You're welcome. Sure, Ivy, go ahead.
I can't find the raise hand option on the Zoom. So I was just wondering, have you run the CanEM 5.2 model with the newest updates in PI control and 4 times CO2? Have you calculated the climate sensitivity of it? And how are you retuning for all of these changes?
So we are currently tuning the model to present day. Also, we are trying to get the present day right, and we are still in the process of that. Once we get a climate that is appropriate for a present day, then we will run PI control and 4 times CO2 to determine the climate sensitivity and use that probably as an extra tuning parameter or an extra tuning metric that we try to achieve to not be an outlier somewhere around 5 or 6 Kelvin anymore.
Okay, thanks. I look forward to those updates.
Yeah, as I'm saying, later this year, it's probably the time.
Okay, thanks, Carsten. For sake of time, we're already a bit over. Let's kick it over to Vivek Arora to present on the new CanESM6 land surface component.
Thanks, Clint. I will share my screen. Okay, can you see my screen?
Yeah, we can see it.
Okay, all right.
Okay, go for it.
Okay, all right, thanks. Okay, so I'm going to talk about the land component of CanESM 5 of CMIP 7. For CMIP 7, And of course, this is a team effort, and the land group at Climate Research Division includes people not only from CCCMA, but also from Climate Processes section. Okay, so I just want to start off by showing this schematic that shows that the model has grown over the years, and in the past, of course, it did only the water and energy fluxes, which is what you need for the physical processes. But over the years, we have included carbon cycle in the model, and now the model also has nitrogen cycle. We have a standalone version of the model that we run offline all the time operationally for global carbon projects. So, and it's always at the bleeding edge. And over the past several years, we've been trying to put the new model version into CanESM, and it's a very technical exercise. And a lot of you here probably would know that the physics component of the model was written by Dinah Versaghi in 1990s. Dinah has now retired. And then in early 2000s, we put in the Canadian terrestrial ecosystem model, which was the carbon cycle, the biogeochemistry component. And that's why the older version of the model is called Class CTEM. And we transitioned to the name Classic after Dinah retired, because the physics and biogeochemistry are so tightly integrated. And Classic was launched as the community model in 2010s, and we added nitrogen cycle in around 2019. So like I said, the model does energy, water, CO2, methane, and nitrogen fluxes as well. Okay, so the number of plant functional types in Classic remains the same as in Class CTEM. It has, for physics, it has 4 vegetation types or plant functional types: needle leaf trees, broadleaf trees, crops, and grasses. For biogeochemistry, you have to divide these into their evergreen and deciduous versions, because you need to know when you are photosynthesizing. And crops and grasses are divided into their C3 and C4 variants, which is 2 different ways of photosynthesis. And the primary prognostic state variables on the physics side in red color here are, of course, the liquid and frozen soil moisture content, soil temperature, and the thickness and fractional coverage of a single snow layer. On the vegetation side, of course, you have vegetation carbon, soil carbon, and you also have, now you also have vegetation and soil nitrogen. Okay, before I go a little further, I just want to give a brief introduction to vegetation dynamics. So the way I think of this is that there are 2 aspects to vegetation dynamics. The first one is, if you have a prescribed coverage of a vegetation in a grid cell, then the model vegetation grows and dies according to the climate. So what this does is, and this is this top example here, what this does is it makes the vegetation structural attributes, leaflet index, vegetation height, rooting depth, and canopy mass a function of climate. And this is what we currently have in CanESM. However, there's another aspect to vegetation dynamics, which is the horizontal one, which is, as the climate changes, the vegetation is able to expand horizontally, change its geographical distribution. And I've tried to show this in the slide, in this graphic in the bottom right panel here. And we do not yet have this. We have this offline working, but we do not have this in the climate model yet. So I just wanted to mention this. Okay, so what we have done, and this is available in version 5.2 that Carsten mentioned, is we went from only 3 soil layers in Class CTEM. The top layer was 10 centimeters, second layer was 25 centimeters, and then there was huge thickness of the third soil layer, 3.75 meters. And that configuration, it served us, but it did not do permafrost properly. And you can imagine, because the third soil layer is so thick. And to do permafrost properly, you have to have, 1, you need to go deeper because there's the thermal inertia. And 2, you have to have a better discretization in the top. So what we have done now is we have 15 layers in the top 4 meters of permeable soil depth. And below that, we have 58 meters of 5 layers of bedrock. And the thickness, this huge thickness of the bedrock layers, it provides the thermal inertia that we need to realistically simulate freezing and thawing of the soil layers, and the higher or the finer profile of the soil layers here, it allows us to do permafrost more properly. So as a result of those 3 soil layers, which were not sufficient, we were one of the poorest models in terms of simulating permafrost extent for CanESM2. This is for CMIP 5. So this is for CMIP 5, and you can see the permafrost extent for the year 2005 is around 15 million square kilometers, and we were around 3 million square kilometers. And our offline simulations show that when we have this profile with 15 soil layers in top 4 meters, then we started around 16.5 million square, and as the climate warms over the historical period, we around year 2005, bang on, we are 15. Of course, this is a coincidence, but the model seems much more realistic in terms of permafrost extent. So when all this is evaluated in the coupled model, we're hoping that permafrost extent would be better than 3 million square kilometers that we had for CMIP 5. The model also has fire now amongst all the biogeochemical processes, and it classically calculates both area burned and emissions due to lightning, as well as due to anthropogenic ignitions, which depend on population density. We also have fire suppression, also as a function of population density. And this slide on the right-hand side of this plot rather shows area burned when you drive the model offline with 2 different observation-based estimates, and the black line is observation from GFED. One thing is we do not capture this peak in fire in boreal forests. Clearly, it's nothing compared to what happens in the tropics, but we do miss this peak here, and work is underway to improve this area burned at high latitudes, including in Canada. And we've had some success in this in our offline runs, but we need to bring that science back into CanESM. Okay, and here is a plot of area burned in pre-industrial runs. CanESM 5 versus offline. So on the left-hand side, you have the area burned in CanESM 5 runs. And on the right-hand side is what we simulate offline. And you can see the model is, even within the framework of CanESM 5, the model is able to reasonably simulate area burned. We have a little bit more area burned in South America. And as you can see, most of the action happens in Africa, the savannas north and south of the equator as the ITCZ moves up and down. So this is what area burned looks like. Okay, so moving on, this is what we are really working towards, is that include nitrogen cycle in the model. And the reason for that is last time around for CMIP6, the land carbon uptake for CanESM 5 was one of the highest amongst all CMIP6 models. And this is despite reasonable performance over the historical period. We have nailed this down to the fact that we did not have nitrogen cycle in the model. So we've been working very hard to include nitrogen cycle in the model. And just like carbon cycle, you have photosynthesis, carbon coming in, and all the respiratory components which return the carbon back to the atmosphere. On the nitrogen cycle, you have biological nitrogen fixation and nitrogen deposition. Those are the 2 ways through which nitrogen comes into the system, and the way the nitrogen leaves is ammonia volatilization, N2O, NOx, and N2 emissions, and nitrate leaching through base flow. And what we have done is we have made photosynthesis rate a function of leaf nitrogen content. So that is how nitrogen constrains photosynthesis, so the model doesn't go crazy as it sees increased CO2 going in the future. And one example here is, this is a study that we did again offline, and over the historical period, you can see that CO2, the effect of CO2 is in blue here. To get the right estimate, and that's this black dot, the effect of all the drivers, CO2, climate, nitrogen deposition, and land use change, you can get the right answer, the black dot, which compares really well with the observation-based estimate, which is the red dotted line of cumulative carbon uptake over the historical period. But to get that, you have to have a higher CO2 effect over the historical period. And the reason for that is over the historical period, part of the carbon uptake also comes from nitrogen deposition, and that's this yellow bit here. So if you don't have the yellow bit, you have to increase your historical carbon uptake. So you have to increase the strength of your CO2 fertilization effect over the historical period to get the right black dot.
2-minute warning.
Now,
Vivek.
okay, but when you do future simulations with those same parameterization, the result is if with the carbon cycle only model, you end up sucking up more CO2 over the future periods because you don't have the nitrogen cycle in. I'm rushing through this now. And the model is capable of taking into account land use change. So going into the future, the areas of trees, grass, and crops change, the population changes. This is the data that model reads in. So we are hoping before the CMIP7 fast track model, we will have the 20 soil layers and fire, which are already included, plus nitrogen cycle evaluated. After the CMIP7 fast track experiments, the MIPS will be continuing. So the hope is we will be able to put competition between plant functional type to simulate the horizontal vegetation dynamics as well. All right, I will stop here. Thank you.
Thank you, Vivek. And I will open it up. Anyone? So there is a question in the chat. We'll just start with that, Vivek. Is N deposition only atmospheric deposition, or does it include application of fertilizer?
Actually, it does. Yeah, so I forgot to mention that. Yes, yes. So there is both nitrogen deposition and fertilizer application. Yes.
Thank you.
All right, then I'll stop sharing my screen.
Yeah, we're not seeing anything else. Neil, can you bring your presentation up? And we'll just see as other people will be bringing it up here. Otherwise, we'll get started here. Okay, presenting next will be Dr. Neil Swart on developing CanESM6, prepping for CMIP7. Since we have no more questions, Neil, I'll have to take it away.
Okay, thanks very much. So yeah, as with all other components of CanESM, the development of the full system model is of course a big team effort and represents the contributions of a lot of people. So I just want to put a shout out to all of those that have contributed. So today I'm going to basically speak about a brief review of the major components of CanESM6, talk a little bit about the coupling of those components together and how we check for conservation, and then talk about incremental testing of all these new big features that we've brought in, how they affect the climate, and then wrap up with some talk about CMIP7 planning. So we've heard a little bit about CanESM5 that we submitted to CMIP6, that we had that model ready about 2018. In 2021, we had an update to that I've spoken about in previous CMOS sessions, where we had basically new technical features and a retuning of the model. We also submitted CanESM5.1 to CMIP6. Carsten mentioned some of the updates that have gone into CanESM5.2, and Vivek talked about the classic update. So these things, together with an update to the version of the ocean model NEMO and some physics upgrades, will form the basis of the new model CanESM6, which we intend to use in CMIP7 and starting end of 2025. So just to draw out a few other things, besides the physics that Carsten talked about in the atmosphere, CanESM6 will also include a new dynamical core based on GEM, and it'll also, along with that, have a new grid, the yin-yang grid shown there. For land, besides all those things that Vivek just spoke about, we are also moving river routing that used to live on the atmospheric grid into the coupler and doing it at a higher resolution. And then, as I mentioned, we're going to be upgrading the ocean model to NEMO 4 or maybe even NEMO 5 if it's ready in time, a new sea ice model, SI cubed, and really a reconsideration of how we're doing sea ice thermodynamics in the coupled system. So that will form the basis of CanESM6. And so those are the components, but we can configure those components in different ways to have different resolutions, to turn on or off different physics, and to tune a set structural physics with different parameters. So there could be quite a few different variants of CanESM6. So how do we go about this task of building an ESM? So super briefly, what basically happens is that there's independent development in the different working groups for each component, like for the atmosphere or for classic and for the ocean. The Earth System Model working group then couples the new components together and verifies that they basically are working together. There's a technical process and there's a scientific process associated with that. And this really involves carefully matching what I would call the coupling interfaces of these different components. What does every model expect? What is every model able to provide? And so once we do that and we look at it and we iterate many times over this, then the ESM goes to be retuned kind of as the last stage of finalization. So let's talk about how we do that coupling. So in the model, there's basically no longer coincident grids. So the red here might give you an example of the atmospheric grid, and the blue might be, say, for example, the ocean grid. So they're not coincident with each other. So what we've moved towards in CanESM5, and we'll maintain that, is that CanAM uses a fractional landmask, which is derived from the NEMO binary landmask. So most of the fluxes in the model are computed within CanAM, so fluxes of heat, evaporation, precipitation, and the runoff, as long as the momentum fluxes are all computed in CanAM. The only flux that's really computed in the ocean/land is the CO2 flux. So when things are computed, they're gathered in the kind of coupling interface of the component model, and then they are passed to the coupler. And the coupler has to do some pre-processing, and that is to convert fields that it's receiving. For example, CanAM might provide some fields, but NEMO wants to receive something else, and those things might not be a direct map on each other. So there's some kind of combination or transformation of variables to match the expectations, for example, of NEMO, which occurs before the remapping or after the remapping. But then there's also a discrete remapping step to transform the variables from the CanAM grid in this case to the NEMO grid or vice versa. And then, it's passed on to the other model, which will then scatter the fields onto its grid and it proceeds. So this goes on in a parallel kind of workflow, and currently we have a 3-hour coupling cycle. So just a reminder from my last CMOS talk that when we go to this yin-yang grid in the GEM dynamical core, which CanESM6 will be based on, it's composed of 2 local area models. And there's never a point within that GEM setup that there's actually a global definition of a field. There's always only definitions of fields like temperature on 2 local area models. These can be kind of overlaid on top of each other, and they have this kind of overset. But that's just a graphical representation. In reality, in the model, there's just 2 different lambs that are running. So this presents a real challenge for coupling, and how do you do it particularly conservatively? And so I described in my last talk how we had come up with kind of a bespoke remapping method in order to transform these yin-yang fields onto the ocean grid, for example, a global ocean grid. So we've come up with this custom approach. It's really important that we check that we're not breaking conservation, which is something that's very important to us in climate, but for example, not so important to our colleagues in weather prediction who have used this yin-yang configuration for some time. So we can look at conservation in terms of fluxes coming through the coupler, and we can compute the integrals on both sides of both that remapping and the processing. So this is just an example for the surface ocean net energy heat flux. So there's some fields from CanAM which represent that, and there's some fields on the ocean side which represent that, and we can compute the global integrals of those. And the top panel on the right is showing the global integral of these heat fluxes in the yin-yang grids in blue, and then in NEMO in orange. And the bottom is showing a relative difference between those, which on average is less than 0.1%. The bottom left panel is the same data as the top right. It's just an XY scatter. So basically, it looks pretty good. We're generally trying to make sure that we're conserving through these kind of integrals to like machine precision, essentially. And so yeah, it's always a work in progress, but I think the method that we have for this is working quite well. The second thing that we like to check very carefully is conservation within each component. So mostly here, I'm just giving an example from NEMO. So we know what the fluxes that are coming in from the coupler, and then we know the reservoirs of heat within NEMO, like the liquid ocean, the snow, and the ice all contain some heat. And then there's fluxes between those. And the right panel is just basically comparing, if we compare the fluxes at the surface relative to the tendency of those reservoirs, do those agree? That would be the definition of conservation. And the bottom right plot, the lines are all on top of each other, so suggesting, yes, in NEMO 4, we know that what we're putting in is being reflected in the state variables. So this is just an example from NEMO, but this has to be evaluated in every component, and particularly with GEM discretized semi-Lagrangian dynamical core, this is really an area of active investigation and potentially concern, because semi-lag is not kind of natively conservative. So we can look at each component, we can look just strictly across the coupler interfaces, but the real thing that we're aiming for is to get conservation across the full ESM, across these components. And ultimately what that would really mean is that the top of atmosphere flux, like the flux from space, is essentially equivalent to the change in ocean heat content. Like the reservoirs of atmosphere and land and ice are relatively small. But yeah, you could include those, but those are kind of like third order terms. So when we do this is a process that we're continuously going through and checking. And just to point out to people that might not think about this, it's actually quite complicated, because it's not just the fluxes of heat. There can be things like the flux of snow, which occurs across the interface between the ocean, or atmosphere and ocean, as a mass flux, but it actually includes an implicit heat flux of latent heat that is released in the atmosphere during fusion and then consumed in the ocean as that snow is melted. So you have to take into account all these kind of things, and it can get pretty complicated to close those budgets and convince yourself you're doing it right. But that's what we spend a lot of time on. So as we've added these new components that I was talking about, and that various previous presenters have spoken about, we do this in a parallel way. So we started with CanESM 5.1, and on top of that, we do CanESM 5.1, and then only add Classic, or only add NEMO 4, or only add the GEM dynamical core. And then we independently combine all those things together so that they all wrapped up. And so doing this is kind of very measured. It gives us traceability to know if a big change occurs, where did that change come from? And it also gives us multiple fallback options. So if one thing doesn't work out, if NEMO 4, we can just never get it working to our satisfaction. It doesn't. If we had just thrown everything together at the beginning, it would be very hard to undo that. But because we've done it independently, we can mix and match these things however we want. So here's an example of PI control simulations using various different of these options. So you can see that Classic, in this case, doesn't change the climate much. NEMO 4 warms it up a bit. GEM warms it up quite a lot. And when you combine these things together, it's even warmer still. So we can kind of tell in this example, okay, a lot of that warming is coming from GEM. As Carsten was saying, we're not particularly worried about this. Like, this is typical of model development. These things are completely untuned, so a lot of these differences will get tuned away. But this is just at the point of allowing us to understand where things are, where and how things are coming from. This is just another example using ENSO variability. So, for example, the CanESM 5.1 model has quite low variability of ENSO across the seasonal cycle. Both NEMO 4 and GEM tend to increase ENSO variability, and the combination of them has actually a very high ENSO variability. So we're always asking, like, how much of this is due to structural changes? How much of this is just due to how the model is tuned? How sensitive is it going to be to tuning? And do we understand why this is occurring? Okay, so just quickly on CMIP 7, they've broken it up into different kind of components. There's the deck kind of core simulations, and there's the fast track, which is intended to serve the IPCC report, and there's a deadline of December 2026. And then everything else is lumped into community MIPS. And so at CCCMA, we've basically already committed to doing DEC plus most of fast track in the ESM working group. And then coming in this fall, we'll have an internal consultation to start planning our engagement with those community MIPS, but also to ask what model configurations are going to best serve our scientific needs in that exercise. And so if members of the community are interested in engaging, you have a MIP that you're really passionate about and you'd like to engage with the CMIP 7 contribution, then please get in touch with me, and yeah, we can talk about bringing you into that process. And our timeline looks a little bit like shown on the bottom, basically finalizing or freezing the model basically at the end of this year, giving ourselves a good amount of time for tuning and evaluation, and then starting that fast track production at the beginning of 2026. So that's it. Thank you.
Thank you, Neil. That I'll open it to questions. If anyone wants to post anything in the Q&A, I'll read it out here.
Jump in because I don't see any questions. Thanks, Neil. This is actually filling a really good gap in some of our earlier sessions that we've had about CanESM and just getting insight into that tuning process. So compared to previous rounds, it sounds like the coupled tuning is going to be like somewhat harder because you're bringing in so many pieces. I don't know, it's not really a question, it's like a comment. It seems like that's going to add, you know, by itself, that could add like quite a bit of time, but it seems like that's worth it. I mean, it really does seem like you've got a process there. Is there any thought? I guess my one question is there any thought to I know you're thinking about this, but if you could comment on automation of this process of like continually, you know, having to retune, recalibrate, and so on. I know there's some thought on automation going on, and be curious to hear about that.
Yeah, I don't know about automation per se, because yeah, but there is a very extended exercise. Carsten's very involved in it, but kind of really led by John Sunoka, which is designed to make the tuning more objective than it has been in the past. As far as you can take that, it's always subjective to some extent, but they call it a parameter screening approach, and it's based on history matching, trying to rule out implausible versions of the model and then leave over others that you can select from. So yeah, it's a new approach. We're testing it right now with CanESM 5.1. It's been tested. It's been now really, that's the way that we're trying to tune CanESM 5.2. So that's going to give us a lot of experience and bring us a lot of the way to the CanESM 6 tuning. And so then hopefully by the time we get to doing it for CanESM 6, I'm not sure I would say it's going to be automated, but at least we would have a very set procedure that's relative, like, or more objective, and that can be deployed, you know, hopefully relatively quickly. Yeah.
Yeah, thanks for distinguishing between automation and objectivity, because you probably need some sort of objective algorithm before you can automate it, and so that makes a lot of sense.
Thanks for the question, Paul. With the time, Paul, we can pass it over to you. We've seen no more questions in the chat, so if you want to bring up your screen, we can get started.
Okay. When I go into, what do you see, my slides?
You see presentation slides now.
Yeah, but starting with the wrong one, right? Okay.
Yeah.
There we go. Okay. Yeah. Okay. All right. So this is not a science talk. This is a talk talking about our larger project called the Collaborative Platform for CanESM, CP4C. I've given updates on this project over the last couple of years in these sessions, and this is our progress report for 2023, 2024. I'd just like to thank my collaborators in this. Katie Terry is a project manager working with me here at the University of Toronto and collaborating a lot with Neil Swart and Clint Seinen at CCCMA. And then the other names listed here are in the steering committee, Paul Myers, Ivy Tan, Matthew Toohey, and Kirsten Ziegfeld. And so they're helping oversee this project. So just to start with to set a frame first for CP4C, we start with CanESM. We've heard quite a bit about CanESM in this session. It's Canada's flagship Earth system model, representing almost 50 years, I think, of development of public investment in Earth system modeling in Canada. CCCMA's model is an independent and kind of genetically independent version of Earth system model in the setting of the Earth system model space, as Carsten mentioned. And there's lots of spin-off applications of CanESM. So it's both, a model for scientific assessment, but also for operational use, for example, in seasonal to inter-annual prediction. And so our project, CP4C, starts with the initiative that CCCMA has undertaken in the last 5 years or so to do an external port of the model. So that leads me to the collaborative platform for CanESM. This is the academic community's research platform to use CanESM. It's a sponsored project of ARCU, which is atmosphere-related research in Canadian universities. It's a special interest group of CMOS, and we're attending a CMOS meeting today. And we have support in different forms. It's largely a community effort, but we have support from the Digital Research Alliance of Canada. The Alliance provides a platform for our computational work. And the overall aim is to increase Canada's capacity as a whole in Earth system model development, application, and analysis. So here's kind of a vision slide. The vision is that what we're trying to do here is enable collaboration between ECCC and the academic community and other community members in industry. So how do we plan to enhance collaborative use of CanESM in a way that reflects the best practice in the use of Earth system models in climate science? Climate science, using Earth system models is a complicated business. So what we need is a technical workflow to be able to use the model in a well-justified way. We need good documentation, realistic examples for people to use as templates to get started with the model. We need some sort of computational resources to run the model. And also assist in the documentation. We're running on HPC, high performance computing platforms, and so we need ways of documenting those runs. And we also want to develop a workflow so that the community that's using that model can collaboratively develop the model. And so we need a workflow for that as well. And finally, to pull this together, we need some policies, all right, which are just ways of documenting how you go about doing this in a way that represents true collaboration. So just to update this slide, these yellow, green, and red lights indicate sort of where we are in the project. So yellow means we're in progress, green means we're kind of accomplished. So the technical workflow, the documentation is in progress. We have some good examples now. We are developing a use policy and a support policy that I'll talk about later. We really aren't in a position yet for the external community to contribute collaboratively to CanESM, but that's where we're aiming. And we do have these modest resources through the Alliance, formerly Compute Canada, to actually do simulations with CanESM, at least in testing mode. So this is a bit of detail, and I won't go into all of it, but basically we've been working for about getting on to 5 years now. Neil did the initial porting of CanESM to the Compute Canada platforms, Cedar and then Niagara. We held a lot of discussions initially. We surveyed the community. We've held different workshops that are I'm listing some of them here. The idea of CP4C itself was part of a proposal we wrote to Compute Canada for a research portal and platform, and we've held several of these Earth system modeling in Canada sessions at CMOS. Believe it or not, this is our 4th. Just as part of our setup, Neil set up this our GitLab site, which is with the URL given here. And this kind of is our basic documentation of how to get started with the model. And there's lots more material being posted there weekly. So last couple of years, just for this talk, we have established a working group, which I'll mention in the next slide as well. We have a steering committee mentioned initially, and then a draft collaborative agreement. We have also a proposal for grants and contributions funding for a period of 4 years, and that's pending, and we should hear news about that this summer. And we have the working group meetings are ongoing. They're bi-weekly. Last year we held our 3rd collaborative ESM session in CMOS. And then in 2024, I think the key things that have happened so far this year are that Clint and Neil have completed this post-processing diagnostic workflow. This is basically an effort to get the output of CanESM into a useful form. And this is actually a unique resource. The useful form is the so-called schemerized version of the output of these Earth system models. This is the standard archived form that you can find for distributed information from Earth system models. And the fact is that the CP4C version, the collaborative version of CanESM, now produces this inline as it goes along. So this is really useful because it means people can get going right away analyzing output from their CanESM simulations. We also held a workshop this year, which I'll talk about. And the rest of the points here are related to our upcoming plans, and including finalizing our collaborative agreement and proposal to renew the CP4C allocation on the Alliance platforms. So this is just an invitation to join the working group. We have all career levels, students, postdocs, faculty are join this discussion. It's a really good sort of technical overview of what's going on, and we're hearing project reports as well on how people are using the model. I have a couple of emails here that I'll show again at the end, but please feel free to contact me at any time if you want information about CP4C. Our workshop in 2024, looking at the time here, it looks like I have about a couple minutes left. Our workshop was really great, actually. We had a 3-day workshop online, included people gathered in-person clusters at several universities like U of T, McGill, Dal in Saskatchewan, and I think there was a group out at UVic as well. So the CCCMA group gave a nice overview of CanESM as an Earth system model. They gave practical instructions on how to use CanESM within CP4C as a kind of walkthrough. And then on the day 3, we talked about CP4C and the various projects we have running on it. So this was all like aimed towards enhancing everybody's background knowledge about Earth system science with CanESM, growing our community of practice, and also getting ideas on this proposal we need to write in the fall for more computer resources. Everything is being posted online. We're actually still sort of processing some of the videos, but it'll all be posted online very shortly, and everybody will be able to access the materials from that workshop. We had a lot of participants. We had 70 registrants, about 50 people a day were attending online and in person, 50, 60. And it was from all across Canada. This was great. And also this is a breakdown down here of the participants. Most of the plurality of participants were graduate students, but we had also postdocs and faculty and undergrads and government staff. So it was really nice kind of cross-section of people interested in this work. Just to highlight here, the really key point is that you can right now use CanESM outside of ECCC to do your science if you have a computer allocation and you're willing to get your hands dirty. All right, so this is just some examples. Haruki Hirasawa has been using CanESM to study marine cloud brightening. Here's the response to marine cloud brightening with CanESM and a few other models. In my group, Anson Chung with Francesco Passata has been looking at the climate effects of nuclear war. And also in my group, Luke Fraser-Leach has been looking at the effects of regional forcing of anthropogenic aerosols within the regional aerosol model into comparison project. And this is all just preliminary work going on right now. These are early days, but it's very encouraging that people like Anson and Luke, who are pretty new students, are actually able to get going with the model and contribute to its development in this platform as well. This document here is this slide here shows just the title of our document, our policy document towards a collaborative agreement between ECCC and CP4C. All right, this is okay. Yeah, so I'll just run through this, and just to say that this is kind of a framework for how we're going to work with each other. A key point is that CanESM is centrally managed by the federal government, right? And I think actually Neil's talk and the talks you heard before that really highlight how technically involved and how much resource is required to calibrate and set up one of these models. But that leaves lots of room for external collaborations. And what we're trying to do is kind of create a framework for efficient and collaborative use of that model. So that means that we have to write out our expectations for documentation, for support, for resources, that kind of thing. So we're trying to write all that down in a way that's accessible, friendly, and also very useful, and something that'll last for several years. So it lays out both kind of the principles, and then we have an implementation plan of a couple of pages talking about what CP4C is, talks about our working group, our regular meetings, and that kind of thing. And really importantly is the idea that as you engage with this model, it's a really good idea to register your participation, register which projects, like how you plan to use the model, and any technical issues or technical needs that you anticipate, so that at least we can know what people need. We can't guarantee, but we recognize that support is limited, and so we're trying to prioritize the way resources are allocated for support of this external collaboration. So just to finish, all right, CanESM is an amazing Canadian product. It's heavily used, it's heavily cited. It reflects, it says 4 decades here, almost 5 decades now of investment and effort, right? So it's a national resource. And what we're trying to do here with CP4C is work with ECC's initiative to extend the user base and potential of application and development for CanESM. We're using it right now for research, all right? It's becoming a research tool that we can use externally. Of course, it is a research tool that people have used for a long time within ECCC, but we're able to do this externally, and that's really important. All this work is highly collaborative. I would say most of the projects we have do have strong points of contact within ECCC. That's an important part of all this, but it really means there's lots for us to do from the university side and certainly from other institutions as well outside the academic sector. So you can get started too. All right, get your hands dirty and come to our working group meetings and get in touch, and we'll try to get you set up quickly. Okay, thanks.
Thank you, Paul. Thank you to everyone else. I will now open the question for Paul's presentation. Feel free to put anything in the Q&A. Ivy, I see your hand raised. While we wait for the Q&A to fill anything else, go for it.
Hi, yeah, I have a question following both Neil and Paul's talks. For Neil's talk, I was just wondering for, in terms of the resolution of CanESM6 that will be run for CMIP 7, I was wondering what the resolution will be, given that I think that basically ECCC has, or the CMA has committed to running a lot of experiments. So I was wondering at what resolution it will be run at. And then also for Paul, my question, sort of following on this development of CanESM, is for CP4C, I guess, in terms of the lag of updating CanESM with the new updates that are ongoing, what can we expect in terms of how we will proceed with updating our versions on Compute Canada or on the DRAC?
Mm-hmm. Neil, did you want to handle the first question, and then I can talk about the second?
Sure. I mean, I guess if the answer quickly is we don't 100% know. I think the intention is to have a 1 degree workhorse model, 1 degree atmosphere, 1 degree ocean that will do the vast majority. But I kind of rushed through it on the last slide, but I was mentioning earlier, we could have different configurations. So we might have a high resolution version that's like a 1/4 degree that we might do limited experiments with. And we might have like a different model, like a chemistry version of the model with more complex physics, for instance. But yeah, that part is what's going to be decided in that full workshop. Exactly. Yeah.
Yeah, and about the lag, I think the way it's interesting, CP4C in some ways has also been testing some new functionality of the whole modeling system, like the running environment for CP4C or for CanESM under CP4C, as you know, Ivy, is different. So actually, I think it's going to be a matter of the prioritization and the scientific validation of new versions of the model. And so I don't think it's a simple question to answer. One example of something that's kind of neither CanESM 6 or CanESM 5 is the work with PAM that's going on inside CP4C. So there's a version of the PLA aerosol model that's being ported to the collaborative version of CanESM under CP4C. And that's an example of a separate sort of testing of a piece to look at how the aerosol physics changes affect basic aspects of the simulation. So that's not really an answer to your question. I don't think we're quite there yet as to figuring out. To me, it seems like what we need to do is look at like 5.1 was ported first, and then a bit after the 5.2 is ready. Sorry, 5.0 was ported first, and a bit after 5.1 was ready, it came under. It was ported over to Seinen, and that was. I'm guessing it was a matter of about 6 months or so. I think one of the bigger changes, though, is like all the system changes, all the infrastructure changes, alongside the physics changes that happen. That might be the rate limiting step. And I see Clint nodding. He'd be probably the right person to ask. So I think we have to be careful with our expectations. And what I'd like to say is we should exploit each version of the model as it comes along, and see what we can do to make sure that we're exploiting the current versions, right? Like we're not just waiting for the latest and greatest, but also exploiting the past versions. And then as we get more experience, I think the motivation to port and the feedback that goes back into CCCMA, that will become a driver for sort of making that port to the CP4C or to the external platforms kind of something that they just do routinely. But for right now, I think it's a matter of, I would say, I'm guessing at least 6 months lag, but I would guess even, it could be longer, but it wouldn't be 2 years, right? It would be more like 6 months to a year. And that's a guess.
Thanks both for your answers.
Yeah, taking my chair hat off for a second. Yeah, it's a tough question to answer at the moment in early days, but eventually we do hope to be reducing the time as well. But in the current initial phase, it's going to be a little longer until we kind of get that process ironed out.
Yeah. Okay. I think we're into our break time now, if I don't.
Yep. I'm not seeing any other questions come up. So I will thank all the speakers for presenting here. And I want to also highlight the fact that session 7031 starts at 11:05 Pacific or 2:05 Eastern. And that will be part 2 of 3 of the session, which Paul will be chairing. So thank you, everybody. And yeah, feel free to take a break and come back later.
Okay. See you soon.